I'll just explain very briefly what it is we're doing here. We're building a new laboratory where scientists can do experiments to study the nucleus of the atom. You may know that what that takes is a big machine called an accelerator. Our accelerator at CBAP is based on superconducting technology, but it's low temperature superconductivity. The subject of tonight's presentation is high temperature superconductivity, which you may recall hearing a lot about, especially a couple of years ago when several advances were made. And to conduct the presentation, here are Dr. Fred Hartline of Christopher Newport College and Dr. Randy Caton. Please help me welcome them.
Well, we're really pleased to see so many of you here. We want to add our welcome to you. How many 7th and 8th graders do we have? About high school. Parents.
What's you get?
We designed this hopefully at a level that everybody can get something out of. If it's a little bit too low for you, don't be annoyed with us. If it's a little bit too high, bear with us. We have a lot of electronic gadgets around here. We have so many remote devices that anything can happen at any time. If we press the wrong button, we have wrong buttons and so on. Hopefully it'll all be great. Before Fred and I tell you about superconductivity, we want to go back to the beginning of the century and tell you about two important events that occurred around that time that bear on superconductivity. The first thing is the Dewar Wars. There really weren't Dewar Wars, but this was a competition between scientists to liquefy the newly discovered helium. The prize was that the first group that was able to liquefy helium would have at their disposal temperatures low enough to do very exciting investigations, and we'll see the consequences of that. On the English side of the channel, we had Dewar competing, the father of the Dewar, and in Scotland we had Hartline Hans. Fred's going to show you a picture of Hans' apparatus. The winner was Hartline Hans. This is an old-fashioned set of apparatus, a lot of very fancy, beautiful glassware, but very cumbersome and not seen very much in modern labs today. We're going to have our own scientific competition in just a moment. One more event that occurred around that time, or exploration that was being carried out by scientists, was to study the resistance of metals to the flow of electricity. In fact, anything, but particularly metals. If we take a wire and attach it across the terminals of a battery, what will happen is a current will flow in that wire. You probably mostly realize that. The voltage we apply is usually given a symbol V. An analog to this behavior can be seen in the right, mechanical analog, where we take a pump water up and let it go down a slide, come back and be collected. In both cases, the fluids, whether it be water for our mechanical analog or electrons or some kind of charges for our electrical analog, there is some resistance to the flow, whatever is flowing. In the case of the water analog, there's some resistance to the flow of the water down the water slide. Maybe the gravel in the bed or whatever. In the battery, in the wire, I should say, or device, or whatever we attach, there's some resistance to the flow of the electrons or charges. A solid, a metal, can be composed of a periodic arrangement. I realize in the back you may not all be able to see this, of atoms. The electrons that are flowing through there interact with the atoms in such a way that it causes the resistance to the flow of electricity. You want to study that resistance, and that's going to be part of your contest, so you better pay attention to those who are going to participate. Ohm defined resistance to the flow of electricity as the change in voltage over the change in current if you had a nice straight line behavior where you plotted the voltage on one hand, which you got from the battery, against the current that's flowing through the circuit, which you can measure with an ammeter. You're going to be doing that. Now, the important thing to realize, whether you're large or small, young or old, is that the resistance is proportional to the slope of this line. If the slope is very steep, like this, the resistance is going to be very large. If the slope is very shallow like this, the resistance is going to be very small to the flow of electricity, and hopefully you'll see that in the contest. So I think we ought to have the contest begin.
Okay.
and you can see there are...
How about the Caton duo?
No, I've got my own way of figuring it out, okay? First thing we need some people to vary the voltage here to set a certain amount of current going through each of the presents. Okay, so I'm going to toss out some little trinkets here, and the first people who collect these can come down and measure my one of each of the four rings. Yeah, right.
Wait for me.
We want you to decide who the winner is going to be and what is in each present. So I'm going to pick like balance X, and I'd like to the 10 balance out.
Find your dial, and Randy will explain to you how to use the ammeter right here. Okay. One on this side. One on this side. Okay, now I got. Okay. Now the next people we need are some people to read the digital voltmeter and report what the voltage is across the present. And these can go to people in the front row. Someone? Do I have someone else? Okay. Each one of you goes to one of the four presents. Okay, finally the last one I need is someone who's got the ultimate test, someone who graphs the data. Okay, we have overhead pens for you. We have two data sheets and each overhead so you have to graph the data from your person. Now your voltage measurer, how you record the voltage, you're going to write it down on a card and hold it up to the grapher and write it down on the graph. Let's see, who's going to do this? Okay. at your own speed. Whoever gets the data plotted first is the winner of the Caton Tours. Okay, on your mark. Get set.
Yeah, wait to see him first.
Go! Ball start. Go, Mike.
Pickle, Tennessee. Pickle.
There's some interesting crossbow, okay?
Pickle.
Blender!
Pickle. Pickle.
Table saw! Fire! Boy, this is very non-linear. It starts out inconsistent low, it's really low, and then takes off. Earthquake! I have no idea what happened out of this end.
Where's the resistance higher in this graph? Down at the bottom here or in the middle?
Let's see what's in it. Let's see what happens higher.
Pickle. 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 Table saw. Nicely done, Al. Hey, that winner's there.
Coming at the end of the program, remember to bring your tickets in to get your food. Now we're going to go back to the early 1900s. Start with our program on superconductivity. Many buttons. Start by pushing you off.
That light bulb.
Thank you. Remember, we left on having liquefied helium. Let's look at the temperature scale so you have some kind of idea what he actually accomplished. Here's the Fahrenheit scale you're used to. Freezing is 32 degrees. The Celsius you now often see on bank, 0 degrees. Both of these zeros were picked arbitrarily before scientists knew anything about temperature. It really turns out there's a more logical point to pick for 0, which is called absolute 0, where classically all motion ceases.
And that is the Kelvin scale, and that's the one the scientists use. There is a long ways to go from 0. Doesn't look like it here because it's short stuff, but it is a long way. Fred will later show you what it's like in liquid nitrogen. Just realize that ONS was way down here at about 4 degrees above absolute 0. Unbelievably cold. None of us, we hope, have ever been that cold. That's drinking. I didn't want to talk about that. There are no scales there to confuse us. That's one thing scientists sometimes prefer to have one temperature scale, but we have more. One of the first things that ONS wanted to do was look at the resistance of metals as a function of temperature. That's different from what you just did. You looked at what happened to the voltage as you increase the current. It's also interesting to see what happens when you cool it. They expected the resistance of a good metal to just keep decreasing and finally go to 0 because the vibrations of the ions on the lattice sites would slowly decrease until you got to absolute 0. There would be none, and that was what they thought was the main contributor to the resistance of the flow of electrons through the material. What did they see? They saw a finite result. Well, scientists can always come up with explanations. They said, we know what that is. It's impurities, and they were right. Pretty good guess because they didn't know much about conductivity at those times. Then ONS said, I know what we'll do. We'll look at mercury. Mercury can be distilled. It's a liquid just like water. When you get all those impurities out, then we will see the resistance go to 0 at 0 temperature. These are ONS' original data. Notice there's just a few points here, and this is a little snippet in temperature. Here's 4 degrees Kelvin. This is on our absolute 0 scale. 4.5 Kelvin. 0's over there through the wall somewhere. So this is a little section. He would have expected this just to continue slowly on down its way towards 0 up to the wall. But what happened at 4.2 degrees? Just like that. It shot to 0 as quickly as they could see. They could measure it fairly well to 1 part in 10 to the 6th, and they determined that the resistance was 0 at 4.2 degrees. Not 0 at 0 degrees, but at 4.2. This was the birth of superconductivity. ONS rightly named this superconductivity. To give you a feeling for how close this really is to 0, the resistance of copper at room temperature, when compared to the resistance of a material in its superconducting state, is 10 to the 20th, and we wrote that out here for you so you could see it. 1 followed by 20 zeros, larger than the resistance in the superconducting state. That's a big difference, and scientists really believe that the resistance in the superconducting state is truly 0. We just can't measure it any better. In fact, it's amazing that people have been able to get together experiments to show that the ratio of resistance to superconducting and copper is 1 part 10 to the 20th. Let's back up and look at this slide again then and talk about what's really important, at least the first part of superconductivity. What happens is, at some finite temperature, the resistance suddenly goes to 0. So we call this region below what we call the transition temperature, Tc, the superconducting region. We say it's in the superconducting state, just like we say ice is in the solid state. And above that, we're in the normal state. Now, the surprising thing is that the best superconductors are the chromiest normal conductors. The next thing that scientists did was plunk all kinds of things in their dewars to try to see what was superconducting and what isn't.
Yes, it was.
Now, all these things were known at the time in the 30s and 40s even, but I just wanted to get some feeling. Don't worry about the different notations. Everything that's colored in on this periodic table is either a PF or an X. Is superconducting in some state. So the real question now is, why are these not superconducting? Because they're the oddballs, not the superconductors. At first they thought it was maybe a very exotic phenomenon. Let's plot ONS discovery on the computer screen. Find a mouse here. What I want to show you in our little short tour of history is what has happened to the transition temperature as time has marched on. We've got the year plotted along this axis and the transition temperature here. Here's ONS discovery in 1911, the birth of superconductivity, 4 degrees Kelvin. And as I showed you, a lot of elements were studied with transition temperatures. So in between. One of the biggest next discoveries was in 1955. by BArium Yttrium. BArium Yttrium was the premier superconducting chef. He was a chemist. He did discover most of the known superconductors, more than anybody else. He has a tremendous record. This is a picture of him in his lab. Technology has moved forward. You don't see the electronics there, but it also is more sophisticated than what Hans said. The material he found was a material that is in a very special structure called A15. I won't say anything further about that, except that many of us, including me, have spent a long period of our scientific career studying A15. They're so interesting. The first one was an IOB-3 tin, and its transition temperature was 18 degrees Kelvin. They continued to study the A15 structures. That seemed to be where it was at. In 1975, I was at a meeting that was very exciting. Somebody discovered another A15 niobium-3 uranium who had a transition temperature of 23 degrees. The previous record was 20.5 degrees. May not sound like a very big step to you, but it was very exciting to scientists. What happened next? Scientists continued. So I'll hit the continue button here. Period of what I call doldrums. Superconductivity funding almost was phased out. Nothing happened. Nobody discovered a new transition temperature above 23 degrees. Right and left scientists were predicting it was impossible to have a transition temperature above 30 degrees. There were all kinds of theories that backed up these statements. They thought they were right. Now the discovery the reason we're here, of course, is because somebody did find a material that's superconducting at a higher temperature than 30 degrees. It's actually superconducting above liquid nitrogen, so we're going to take a break now. And Fred is going to show you something about liquid nitrogen, and we will demonstrate and talk more about the new superconductors.
Okay. Let's see, I've got a dewar here which has got a bunch of liquid in it. You can see it's sort of frothing a little bit over there. That's actually oxygen water vapor. And what I'm going to do with this is I'm going to boil it in this teapot and make up some tea. So I get myself a flower here, and I'll make a little cup here. But first I got to boil the liquid nitrogen, so where's some in here?
That looks pretty good.
Oh, that looks good. Looks like we got a nice one right now. Okay. So I've got a nice cup of tea brewing here. It's not rosehip tea. It's not the right season for roses. And as you can see, it doesn't seem to hurt the flower too much, except that it does change its properties a little bit. It becomes a little brittle. However, now we'll take this tea and we'll pour some of it for someone here in this cup, like that. And as you can see, it's sitting there boiling away. This is a pewter cup. This is a pewter cup, and it's just sitting there boiling away. Now I need someone to come up. How about you? Very good. Do it, Ken. This cup. Stick and see what it sounds like. That is a different sound. Try the other one. Okay, quite a change in the properties of that metal. Okay. I don't think I'll drink this one, though. I don't think I have to tonight. We've got other metals here, which I'll go ahead and do. I've got and this is a little transformer, just a very thin copper wire wrapped many, many times. And I've got a light bulb in series with it. So what I'm going to do is see essentially what happens to the resistance of copper as I cool down this coil. You all can see that this is not glowing very brightly. Okay. The lights down here, and then I will drop this coil in while Randy is talking about the history. Those of you who don't want to listen can watch and see what happens to the light bulb as the coil cools down.
the view graph that I showed you before, and can't find right now, the resistance of metals slowly goes down as the temperature goes down, and the light bulb is going to glow more and more brightly as the current increases and the resistance to its flow drops. So let's continue on with our story of superconductivity and what happened in 1986. It's called the Woodstock of physics. Before that, two scientists from Switzerland, from IBM, Bednortz and Mueller, discovered a new material. They got out of the A15 rut. They decided they really believed the theorist and we'd never get above 30 degrees Kelvin with A15 material. And so they tried something very around 35 Kelvin. Now remember, 30 was predicted as the, so to speak, speed limit. And now we're up in 1986 to 35. That was really shocking. A lot of scientists around the world did not believe this at first. There have been many false alarms, and it took a while. Also, these scientists were very cautious, which is good. They reproduced their results. They published in a low-key journal. And it really took about a half a year to 3/4 of a year before scientists caught on. Then Paul Chu in Houston subjected these new materials, these BArium Copper Oxide, very complicated structures, to high pressures, and they found that the transition temperature increased. Well, that was a clue to all kinds of people who worked in materials that what you want to do is substitute in a very small atom, like yttrium, is what they did, into the lattice for the lanthanum, and see if you could mimic this effective pressure, which is tending to squeeze the lattice down, by putting a smaller atom in there. And lo and behold, that worked. Paul Chu and Wu and many other scientists, a whole horde of them, right around the same time, found a new superconductor, BArium Copper Oxide, and that's the one that hit the news and you probably all heard about. Has a transition temperature now of 92 Kelvin. Very stunning rise here in a very short period of time, verified by many labs. Notice that it's above the space temperature. This now makes space applications possible, whereas before they would have been impossible because all the transition temperatures were way too low. Now it didn't stop there. Scientists have been working on variations of oxides ever since the '86 discovery, and actually after a few years, they found other superconductors, some with thallium. Thallium is not very nice to work with, it's used in rat poison. But thallium, strontium, calcium, copper oxide, look how complicated it's getting. It really takes trial and error to find these things. There's no theory to guide people. It's up at 125 degrees, and that's where it stopped now. The question is where next, and maybe some of you will be answering that question in the future. There's no reason to believe there won't be more breakthroughs in the future. What we want to do is demonstrate this astounding property of superconductivity at about 92 degrees Kelvin in front of you. So we have a system set up with a sample mounted. Fred's going to tell you about that. We've got a video projector. We're switching to one of our many different devices.
Okay, let me take over.
So Fred's going to tell you about the sample while I get the computer ready to take data on the sample.
And we're going to run you right down, do the experiment right here. We've got all the apparatus that you can see. I've got it on a video camera so that you can see what this grinder thing is a brass block. It's got a screw in it that I'm going to dip into the liquid nitrogen in this dewar. So I'll put the dewar underneath here. We'll lower the whole thing in. What you see up here, this little black rectangle, is a sample of this ceramic BAYCO. And we've got attached to it, you can see 4 whitish dots. Those are 4 little silver beads that go to wires that go off the shaft here to our instrumentation. The outer 2 beads, this one and this one, are where we connect the current that we pass through. We've got essentially a battery that pushes a certain amount of current through that we can measure that's constant. And we're looking for a voltage to appear across these 2 dots. So these inner 2 connectors measure the voltage. If there is a resistance, when you pass a current through the sample, there will be a voltage drop across the inner 2 connectors. So The temperature, you can see we've got a digital thermometer there. That's attached to a platinum probe on the back of this that reads the temperature in the copper block at about the same place. So now let me lower this.
Okay, take one last look at this. We're going to go to the computer now.
Go ahead and lower it in. Let them see the temperature drop.
Okay. Yes.
All right, you can see the temperature is dropping right now, going at a fairly good clip. Let me,
Now all of these data are being fed into the computer by another thermometer. It's basically a thermocouple, and if you're interested afterwards, you can come down and we'll be glad to show you what a thermocouple is. Okay, it's already plotting on the screen. The temperature is on the horizontal axis. Disregard the units, it's an arbitrary unit, it's radiant voltage. The resistance, proportional to the voltage, is on the vertical axis, and we're seeing what's happening to the resistance as the temperature drops. And Fred will continue lowering that into the doer while I go on the remaining time with a little bit more explanation of superconductivity and actually data analysis. Let's back up a minute and look at On's lab again. Just for comparison, 1911, glassware, bolt back, and how many numbers? Fred, sound pretty good? 1955, metalware, more sophisticated electronics, you can't see it. 70s and 80s, here's the refrigerator that we use for our measurements. It's only about 1.5 foot high, it's compact, recyclable. We don't use liquid cryogens like liquid helium. Things have advanced considerably. In addition to that, we have an automated data acquisition system. Everybody has these nowadays. I can find This is a scanner which really just measures voltages and feeds them into the computer. This is a fancy thermometer which also measures the voltage from the thermometer, feeds that into the computer, so now the computer knows the temperature and the voltage, so we can get the resistance. And we see an output on the screen normally. We can print the data to a printer. We can plot the data on a plotter. The data are saved on disks for us to analyze at a later time. What I want to show you is a comparison of data taken with a fancy system like this compared to the upper part first. Notice how much more smooth these data are compared to those data. There's a good reason for that. Whenever you measure something, you get two things. You get the signal you're after, and you get something we call noise, which is unwanted and not related to the signal. In this particular case, with a DC measurement like this direct current measurement, there are large thermal voltages present that are caused by two dissimilar metals being at different temperatures. They are part of what you pick up when you put the probe across the voltmeter. We're just measuring one direction here. The only way to get rid of this unwanted thermal noise is to reverse the current and average. Our computer reverses the current and averages 10 times for every data point. That's why these are so smooth. We don't have any averaging down here. Oh, there it goes. What's happening, right? Back to transition temperature central. Notice how dramatically the resistance changed while I was talking. It was slowly going down like a crummy metal, and finally shot down when it got near the transition temperature. What Fred's going to try to do now is warm it up a little for you so you can see more data points in the transition. Could have.
graphic data points right around 0.
0 is right around here, so what if we continue to go down and actually at 0, and then we can see transition points. Let's see what it looks like from our laboratory system. This is what the transition looks like. It's very sharp. This all takes place within about 1 degree Kelvin, so it's a fairly sharp transition. Below this temperature, the superconductor, above this temperature, it's a crummy metal. Actually much crummier than copper. The interesting thing about superconductivity is the better superconductors are the crummier metals. from your normal conductors. There's an inverse relationship. And the theory of superconductivity does explain that. One more bit before we go on to the final demonstration, then I'll stop talking. By the way, any of you have questions? We really had to go through everything very quickly. I didn't say anything about why superconductivity exists. Please feel free to come down afterwards. Remember, you spent a lot of time taking voltage versus current curves. I wanted to show you a more exotic voltage versus current curve, which is an application of superconductivity. If you take a junction and put a superconductor, this is really a sandwich. Doesn't quite look good enough to eat. I tried to make it look good enough to eat. There's a sandwich. We have a superconductor on the top, an oxide barrier in between, and a superconductor below. If we pass a current through that junction, just like you did in your contact, and measure the voltage across the two sides, superconductor 1 and 2, we get this kind of an IV curve. Very weird. May look like nonsense to you. This junction is using current that is cycling 90 gigahertz. 96 times 10 to the 9 times every second. The current you were using in your contest is cycling how many times every second? What is it? 60. A little bit more. If you put that much, if you put that frequency current into the junction, you get an IV curve like that. The spacing between these lines are really, although it doesn't look like on this graph, are really very well determined. And they are connected to theory with absolutely no adjustable parameters as far as anybody knows. Almost every theory needs some kind of a fudge factor, but this relies only on some very fundamental concepts. Frequency can be measured very accurately, so what the National Bureau of Standards does now is set up a voltage standard for people, and they know exactly what these tick marks are to a precision of something like 1 part in 10 to the 10th. Very high precision. So that's one thing that superconductors have allowed us to do, and that's an interesting application of your IV curves. For the finale, last thing we're going to do is talk about another important property of superconductors, the fact that when the material goes into the superconducting state, it expels all magnetic field. Some of you have probably seen this demonstration before. If we put a magnet on top of the superconductor, the field lines that are threading out of that magnet will become expelled from the interior of the superconductor once it's cold enough. Remember, right now, it's at room temperature. Fred is cooling it to make it cold enough so that can happen. Once that happens, you can imagine in a very simplified view, this isn't quite accurate, but in a simplified view, that in order to expel the field from the superconductor, you have to set up a magnet with exactly the opposite polarity. So if you have north pointing down for your magnet, which in this case is either one of these two little yellow discs or the magnet swinging on the pendulum, you will find that in the superconductor we create the North Pole pointing up and they repel, and we see levitation. Here you see it now. This one is floating by itself. This, you see it wiggle by itself. The pendulum was started out moving in a straight arc. You know, pendulums are very dull. They just keep in there playing forever. But when the material goes superconducting, it may not be quite cold enough, you will see the interaction between this large magnet, that's not a regular magnet bob, that is again another magnet, normal magnet. You can see it starting already, it's changing the plane of oscillation. It's just starting to go superconducting. It will slow down the oscillations of the pendulum. It will make them go in a circle instead of a plane. That is all due to the magnetic interaction of the superconductor and the magnet. It's due to the fact that the superconductor is expelling the magnetic field.
Okay.
Don't forget